We will talk about the normal probability distribution in this video. The normal probability distribution, or simply the normal curve, is also known as the Gaussian curve, as it is named after Carl Friedrich Gauss, who first described it as irrationalized measurement errors. Although some textbooks attribute the discovery of this distribution to French mathematician Abraham de Moivre, because decades before, de Moivre arrived at the same curve when he published the Doctrine of Chances, where he wrote how to model the toss of a coin. Anyway, to illustrate the normal probability distribution looks like this, a bell-shaped curve, and it is just one of the many probability distributions. Graphically, it is like a histogram wherein the observations on the center are the observations which occurred most frequently, and the farther the observations are from the center, the less frequent they occur. To illustrate, for example, We Are Social and Hootsuite reported that last January 2021, Filipinos are using social media at an average of 4 hours and 15 minutes every day, which shows that the mean daily use of social media of Filipinos is 255 minutes. That indicates that if the daily use of social media of Filipinos is normally distributed, most Filipinos are using social media for around 255 minutes.
And they all went to heaven in a little row. Clap, snap, clap, 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 snap, clap.
Hoy, Facebook ka ng Facebook.
Facebook live lang ako.
Tawag ka ni Mama, maghugas ka daw ng pinggan.
Mamaya punta ako sa kusina.
4 na oras ka na dyan, kanina ka pa eh.
The properties of the normal distribution are as follows. First is that the mean, median, and mode are all equal. As we can see on the figure, the one with the highest frequency, which is obviously the mode, is the one in the middle that is assumed to be the mean. And since it is in the middle, then it is also the median. And as we can see in the figure, the normal probability distribution is symmetric around the center, which is the mean, median, and mode. And since the median divides the distribution into 2 equal parts, then the lower 50% of the distribution is below the mean, and the upper 50% of the distribution is above the mean. And as we can see in the figure, obviously, the normal probability distribution has a total area of 100%. Consider that the normal probability distribution extends on both directions towards infinity. Or in other words, the tail of the normal distribution, be it on the left or on the right, are both open. In the normal probability distribution, wherein the mean is in the middle of the distribution, one standard deviation more than the mean is on this part of the distribution. 2 standard deviations more than the mean is on this part of the distribution. And 3 standard deviations more than the mean is on this part of the distribution. And by symmetry, 1 standard deviation less from the mean is on this part of the distribution, 2 standard deviations less from the mean is on this part of the distribution, and 3 standard deviation less from the mean is on this part of the distribution. And of course, we may extend those number of standard deviations more on the left and on the right, since the normal probability distribution extends on both directions toward infinity. So if we have a random variable x which is normally distributed with mean of 50 and standard deviation of 5, 1 standard deviation more from the mean, which is 55, is on this part of the distribution. 2 standard deviations more from the mean, which is 60, is on this part of the distribution. And 3 standard deviations more from its mean, which is 65, is on this part of the distribution. And by symmetry, 1 standard deviation less from the mean, which is 45, is on this part of the distribution. Similarly, 2 standard deviation less from the mean, which is 40, and 3 standard deviations less from the mean, which is 35, is on this part of the distribution. And similarly, for example, if X is the daily social media usage of Filipinos, which is reportedly to have a mean of 255 minutes, assuming it is normally distributed and with standard deviation, for example, of 30 minutes, then 1, 2, and 3 standard deviations more than the mean, which are 285, 315, and 345 minutes, are on this part of the distribution. And by symmetry, 1 and 2 and 3 standard deviations less from the mean, which are 225, 195, and 165 are on this part of the distribution. Thus, regardless of the unit of measurement, any random variable x that is normally distributed may be illustrated in this form, where x is its original scale, and z represents the number of standard deviations that is added or subtracted from the mean. That is, the standardized score z is computed as x minus the mean all over the standard deviation. That is why for this distribution, x as 55 has a standardized score of 1, 65 as 3, and 40 as negative 2. Just remember that whenever the standardized score z is positive, that indicates that the random variable x is above its mean, and whenever the standardized score z is negative, that indicates that the random variable x is below its mean. And note that this distribution having the original scale x with mean of mu and standard deviation sigma, when standardized to z, has a mean of 0 and standard deviation of 1, which is referred to as the standard normal distribution. Thus, regardless of any random variable x, as long as it is normally distributed, may be represented to a standard normal distribution.
Two equivalent tests were given to a group. The tests are designed with different scales. The results are normally distributed and summarized below. Which is better, a score of 145 in test 1 or a score of 60 in test 2? Given that the mean of test 1 is 100 and standard deviation of 15, and the mean score in test 2 is 40 and standard deviation of 5. To determine which is better, a score of 145 in test 1 or a score of 60 in test 2, we just have to know the position of those scores in the normal distribution. Given that the mean and standard deviation of test 1 and test 2, we just have to standardize or get the z-score of 145 given this mean and standard deviation, as well as the z-score of 60 given this mean and standard deviation. And calculating the z-score of 145 given this mean and standard deviation, and getting the z-score of 60 given this mean and standard deviation, we're going to have a z-score of 3 in test 1 and a z-score of 4 in test 2. And from this, we can see that a z-score of 4 is way better as compared to a z-score of 3. Thus, we can say that a score of 60 in test 2 or with a z-score of 4 is better as compared to a score of 145 or a z-score of 3. Similarly, if one got 130 in chemistry and 113 in math, and if the scores in chemistry and math are normally distributed with mean of 140 standard deviation of 5 and 125 standard deviation of 4 respectively, in what course did Juan got better? Likewise, we just have to get the standardized score or the z-score of 130 given this mean and standard deviation, as well as the z-score or the standardized score of 113 given this mean and standard deviation. And getting the z-score of 130, we have negative 2, and the z-score of 113 is negative 3. And based on these results, we can say that negative 3 is way less as compared to a z-score of negative 2. So we can say that a score of 130 indicates a better performance as compared to a score of 113.
We can see on those examples that if we're talking about performance result, a higher z-score is better. But that is not always the case. Because if we're talking about health, for example, blood glucose level, a very high blood glucose level is not healthy. And on the contrary, if we're talking about temperature, a very low temperature will not do good to us. Now, since the normal distribution is a probability distribution, we may compute probabilities associated with it using what we call the normal probability density function. Oh God, that's too much! To make things easier, we're going to make use of the normdis.pdf file, in which you may download using the link below. This file shows a table that gives the cumulative probability of z. When we say cumulative probability of z, that is represented by the area from the leftmost part of the curve or the negative infinity to a particular value of z. Imagine a man pumping some air to the normal distribution. The amount of air being pumped in the normal distribution is the probability, but he is only allowed to pump from the left side of the distribution. In other words, if you want to find the probability of standardized random variable z less than a particular value of z, we may use this table. Just consider that on the table, the leftmost column is the value of z up to its first decimal value, and the uppermost row refers to the second decimal value of z. So for example, if you're looking at the cumulative probability of z at negative 2.73, or the probability of standardized random variable z to be less than negative 2.73, all you have to do is to take a look at negative 2.7 on the leftmost column and 0.03 on the uppermost row. Whatever is the intersection of that is the cumulative probability that we are looking for. Just keep in mind that the total area in the normal probability distribution is always equal to 1.0 or 100%. Let's have examples. Suppose we're looking for the probability of standardized random variable z to be less than 1.20. Now since this is z equals 1 and this is z equals 2, we know that z equals 1.2 is somewhere here. And the area to the left is the probability of z to be less than 1.20. And to find that, we just have to take a look on the table, 1.2 on the leftmost column and 0.00 in the uppermost row. And that gives us 0.8849. Thus, we can say that the area of z equals 1.20 to the left, or simply the probability of z to be less than 1.20 is 0.8849. Let's have another example. Suppose we're looking for the probability of z to be less than 0.87, which is represented by this shaded region. So to do that, we just have to locate 0.8 on the leftmost column and 0.07 in the uppermost row. And we find 0.8078. Thus, the probability of z to be less than 0.87, or the area of z equals 0.87 to the left, is 0.8078. Let's have another example. Suppose we're looking for the probability of z to be less than negative 2.02. So similarly, we just have to take a look at negative 2.0 on the leftmost column and 0.02 on the uppermost row. And that gives us 0.0217. Thus, the probability of z to be less than negative 2.02 is 0.0217. Just always keep in mind that this table that we are using always gives us the cumulative probability, or in other words, the area from the left tail of the normal distribution. So if we're looking for the probability of z to be greater than 1.88, which happens to be the area of z equals 1.88 to the right tail of the distribution, and if we're going to take a look at the table, locating 1.8 and 0.08, that gives us 0.9699. However, that 0.9699 is the area from the left tail of the probability distribution. And since we know that the total area of the normal probability distribution is equal to 1.0, then all we have to do is to subtract 0.9699 from 1. And we get 0.0301. Thus, we can say that the probability of z to be greater than 1.88 is 0.0301. Or in other words, the area of z equals 1.88 to the right tail of the distribution is 0.0301. Similarly, if we're trying to find the probability of z to be greater than negative 2.01, which is represented by the shaded region here, locating negative 2.0 on the leftmost column and 0.01 on the uppermost row gives us 0.0222, which happens to be the area from the left tail of the distribution. And since what we need is on the other side of z equals negative 2.01, and knowing that the total area in the normal probability distribution is 1.0, then all we have to do is to subtract 0.0222 from 1, and that gives us 0.9778. Thus, the probability of z to be greater than negative 2.01 is 0.9778. Now suppose we're asked to find the probability of z to be between negative 2.35 and 1.27, which is represented by this region. For the probability of z to be less than 1.27, that is 0.8980, which happens to be this region. However, that is not the region we are looking for. We have to remove a part of it, which is this small area here, which happens to be the probability of less than negative 2.35. And by taking a look at the table, the probability of z to be less than negative 2.35 is 0.0094. And that is the part of this region that we have to remove. And subtracting 0.8980 with 0.0094, we are going to get 0.8886. And that is the probability that we're looking for. Thus, the probability of z to be between negative 2.35 and 1.27 is 0.8886. And similarly, if we're trying to find the probability of z to be between 0.84 and 1.93, all we have to do is to subtract the probability of z to be less than 1.93 with the probability of z to be less than 0.84, and that gives us 0.1737. Thus, in problems, in finding the probabilities given z-scores, whenever you're trying to find the probability of standardized random variable z to be less than a specific value of z, all you have to do is to take a look at the table, find the cumulative probability, and that's it. On the other hand, if you're trying to find the probability of standardized random variable z to be greater than a specific value of z, take a look at the table, that gives us the cumulative probability, then subtract it from 1. And when you're asked to find the probability of z to be between two values, let's say z sub 1 and z sub 2, all you have to do is to find the cumulative probability of z sub 2 and subtract it with the cumulative probability of z sub 1. Now note here that capital Z, or the standardized random variable, is the set or all the possible numbers ranging from negative infinity to positive infinity. And the small z is an element of that capital Z. Or in other words, z is a specific value which may range from negative infinity to positive infinity. Now for more exercises, you may answer the succeeding items on your own. Just pause the video and resume it once you're done to check if you got the answers correctly. Now on the previous examples, you're asked for some probability given some specific value of z. Now what if it's the other way around? The given is the probability and you will find a particular value of z. Now suppose you're asked to find the probability that a standardized random variable z to be less than a specific value z, let's say 0.01. In other words, you're going to find z in which the area to the left is 0.01. That is, we're going to look for 0.01 or 0.0100 among the cumulative probabilities given on the table. And once found, identify the z-score based on its leftmost column and its uppermost row. And since there is no exact 0.0100, we may make use of the one that is nearest, and apparently that is 0.0099, which is found when z equals negative 2.33. That is, the probability of z to be less than negative 2.33 is 0.01. And similarly, if you're looking for z in which the cumulative probability is 0.05, you just have to find 0.0500 among the cumulative probabilities on the table. However, we may see that there are two values that are closest to 0.0500, which is 0.0495 and 0.0505, which happens to be negative 1.64 and negative 1.65. However, for us not to argue anymore what specific value, either negative 1.64 or negative 1.65, are going to make use of, let us just make use of the middle value of those two values. So instead, we're going to make use of negative 1.645. However, actually in the next video, I'll show you that z equals negative 1.64 is better than negative 1.65. It's because when rounded off to 2 decimal places, the exact value of z that gives the cumulative probability of exactly 0.05 when rounded off is actually negative 1.64 and not negative 1.65. In the meantime, let us just make use of negative 1.645. Thus, the probability of z to be less than negative 1.645 is 0.05. And likewise, if you want to find the value of z in which the cumulative probability is 0.10, you just have to make use of the table and you will see that the nearest value to 0.10 or 0.1000 is 0.1003, which is at z equals negative 1.28. Thus, we may say that the probability of z to be less than negative 1.28 is 0.10. Now, if the given probability is about greater than, which is represented by an area to our particular value of z to the right side of the distribution, let's say the probability of z to be greater than small z is 0.01, which is represented in this figure. We may not make use yet of the table since the table again gives the cumulative probability, or the area from the leftmost part of the distribution. However, it must be intuitive on your part already that if the area to the right is 0.01, then the area to the left of that particular value of z, we must know is 0.99 because the sum of the probabilities in the normal distribution again is 1.00. So the one that we have to find on the table is the cumulative probability, which is 0.99 or 0.9900. And taking a look at the table, we may make use of 0.9901 since that is the closest value to 0.9900. And that is when z is positive 2.33. Thus, we may say that the probability of z to be greater than positive 2.33 is 0.01. And likewise, if you're finding z in which the area to the right is 0.05, or in other words, the probability of z to be greater than small z is 0.05, then all you have to do is to subtract first 0.05 from 1, which gives the cumulative probability of 0.95. And taking a look 0.9500 on the table, the ones that are closest are 0.9495 and 0.9505, which happens to be 1.64 and 1.65. Thus, we may make use of z equals 1.645 to denote that it's exactly between z equals 1.64 and z equals 1.65 based on the table. Thus, we may say that the probability of z to be greater than 1.645 is 0.05. Same thing if we're looking for z in which the area to the right is 0.10. Just subtract 0.10 first from 1 to get the cumulative probability, which is 0.90. Then taking a look at the table, 0.9000 is when z equals 1.28. Thus, we may say that the probability of z greater than 1.28 is 0.10. Now, what you must notice is that the answers to numbers 8, 9, and 10 are similar to numbers 11, 12, and 13. That is again because the normal probability distribution is symmetric around its mean or the center. Thus, what happens to numbers 11, 12, and 13 are just symmetry of numbers 8, 9, and 10. That is why negative 2.33 became positive 2.33, negative 1.645 became positive 1.645, and negative 1.28 became positive 1.28. Now, if you're looking for two values of z, let's say z sub 1 and z sub 2, having an area of 0.90, where z sub 1 is just a symmetry of z sub 2, or in other words, 0.90 is exactly on the center of the distribution, that means that the area on both extremes is equal to 0.10. And by symmetry, we may say that the area to the leftmost part is 0.05, and the area on the rightmost part is also 0.05. And based on example numbers 9 and 12, we must know already that those values of z are negative 1.645 and positive 1.645. Thus, we may say that the probability of z to be between negative 1.645 and positive 1.645 is equal to 0.90. Similarly, if you're looking for z sub 1 and z sub 2 in which the area in between is 0.95, you must know already that the area on both sides of the extremes have a total of 0.05. And by symmetry, you must know that the area on the leftmost tail of the curve is 0.025, and likewise the area on the rightmost tail is also 0.025. So looking for 0.025 on the cumulative probability to find z sub 1, and the total cumulative probability of 0.975 to find z sub 2, and you will find z sub 1 as negative 1.96 and z sub 2 as positive 1.96. So that is the probability of z to be between negative 1.96 and positive 1.96 is 0.95. And lastly, if you're looking for z sub 1 and z sub 2 in which the area in between is 0.99, then you must know that the area on both extremes of the distribution is equal to 0.01. And then again, by symmetry, you must know that the area to the leftmost tail is 0.005 and the area to the rightmost tail is 0.005. Thus, looking for the cumulative probability of 0.005 for z sub 1 and the total cumulative probability of 0.995 to find z sub 2. And based on the table, we have 0.0049 and 0.0051 as the closest cumulative probabilities to 0.005, which happens to be at z equals negative 2.57 and z equals negative 2.58. Thus, we may make use of negative 2.575 as the value of z sub 1. And similarly, to find 0.995, the closest values are 0.9949 and 0.9951, which happens to be at z equals 2.57 and 2.58. So we may make use of 2.575 as z sub 2. Thus, we may write that the probability of z to be between negative 2.575 and positive 2.575 as 0.99. Now, those z-scores that we just found are essential as you move along on topics involving inferential statistics, as those z-scores are actually what we call the critical values for z-tests. Now, on the table of the critical values of z-tests on the leftmost column, we will see what we call the alpha. Now, the alpha on the leftmost column, which we will eventually call as the level of significance, is simply the area to the extreme of the normal distribution. For the one-tailed test column, alpha equals 0.01 indicates that the area to the extreme left or to the extreme right of the normal probability distribution is 0.01. And based on the previous examples, that is either z equals negative 2.33 for left tail and z equals positive 2.33 for the right tail. And similarly, for alpha equals 0.05, that indicates that the area to the extreme left or the extreme right of the normal probability distribution is 0.05. And based on the previous examples, that is either z equals negative 1.645 for the left tail and z equals positive 1.645 for the right tail. And for alpha equals 0.10, that indicates that the area to the extreme left or the extreme right of the distribution is 0.10. And based on the previous examples, those z-scores are either negative 1.28 or positive 1.28. As for the two-tailed column, alpha equals 0.01 indicates that the area on both tail, the left tail and the right tail, have a total of 0.01. Or in other words, we're looking for two values of z in which the area between is 0.99. And we have already found out a while ago in which those values of z are negative 2.575 and positive 2.575. Thus, we're going to make use of z equals positive 2.575 and negative 2.575 when alpha equals 0.01 under two-tailed tests. Similarly, for alpha equals 0.05, that indicates that the area between the two values of z is 0.95. And we have already found that a while ago, which happened to be positive and negative 1.96. And lastly, for alpha equals 0.10, that indicates that the area between the two values of z is 0.90, which happened to be when z equals positive 1.645 and negative 1.645. For another set of exercises, you may answer the succeeding items. Just pause the video and resume once you're already done to check if your answer is correct. Let's now move on to what we call as the p-value, in which according to the American Statistical Association is the probability under a specified statistical model that a statistical summary of the data would be equal or more extreme than its observed value. Or simply, it is the probability that the observed values, in which in inferential statistics referred to as the test statistic, to be at least as equal than the one that was actually observed, given that the null hypothesis is true. Or simply, let's put it this way first. It is simply the area of the test statistics, let's say z, to the extreme.
So when you're asked to find the p-value of z equals 0.70, which as we can see in the figure is on the right side of the curve, then the area to the extreme of that is the right side of the normal distribution. So all we have to do is to get the probability of z to be greater than 0.70 or the area from 0.70 to the right. And taking a look at the table, z equals 0.70 has a cumulative probability of 0.7580. Remember that this is the cumulative probability. Thus, 0.7580 is this area of the normal curve. And since what we're after is on this right side of the curve, then all we have to do is to subtract it from 1. And subtracting it from 1, we're going to have 0.2420. Thus, the p-value of z equals 0.70 is 0.2420. On the other hand, if you're asked to find the p-value of z equals negative 0.85, which is essentially on the left side of the distribution, thus its area to the extreme is its area to the left, or basically the probability that z is less than negative 0.85. And taking a look at the table, the cumulative probability of negative 0.85 is 0.1977. Thus, we can say that the p-value of z equals negative 0.85 is 0.1977. And lastly, if you're asked to get the p-value of two z-scores, let's say positive and negative 1.50, then we have two areas to the extreme, the one represented by this region and the one represented by this region. So we just have to get the area of this region, which is the probability that z is less than negative 1.50, and add it with this area, which represents the probability that z is greater than 1.50. And getting the probability of z less than negative 1.50, taking a look at the table, we have 0.0668. Thus, the area represented by this region is 0.0668. On the other hand, if you're getting the area of this, which is the probability of z greater than 1.50, 1.50 based on the table is 0.9332, which is the area from 1.5 to the left. And since we're after with this right side of the distribution, then all we have to do is to subtract 0.9332 from 1. And still we're going to get 0.0668. Thus, this area, which is 0.668, will just be added with another 0.0668. And we're going to get 0.1336.
The normal probability distribution has many applications. For example, in medicine, they have normal reference range for a specific parameter. For example, in red blood cell count, they have a normal reference range. White blood cell count, they have a normal reference range. Now suppose a certain blood parameter, which is the blood urea nitrogen, or simply as the BUN. Assuming it is normally distributed, having a mean of 4.80 millimoles per liter and standard deviation of 1.17 millimoles per liter, let's try to find the following. Let's start with the first one. Suppose you're asked to find the probability that a random sample has a BUN of less than 2.30 millimoles per liter. And in order for us to make use of the NormDis point PDF table, which gives the cumulative probability of the standard normal distribution, we have to standardize 2.30 first. So looking for the standardized score z, we just simply have to subtract 2.30 with the mean, which is 4.80 millimoles per liter, divided by the standard deviation, which is 1.17 millimoles per liter. And that gives us a value of z, which is negative 2.14. So in short, the probability of random variable x, which is the BUN, to be less than 2.30 is the same as the probability of the standardized score z to be less than negative 2.14. And by using the table, we can see that the probability of z to be less than negative 2.14 is 0.0162. Now, to find the probability that a random sample BUN is greater than 5.97, similarly, we have to standardize 5.97 first, and that gives us a value of z, which is 1.00. And by taking a look at the norm disk point PDF table, z equals 1.00 gives us the cumulative probability, which is 0.8413, which is the area of 1.00 to its left. And since what we're after is on the other side, then we just have to subtract 0.8413 from 1. And that gives us 0.1587. Thus, the probability of x to be greater than 5.97 is 0.1587. Now, to find the probability that a random sample BUN is between 2.11 and 7.14, similarly, we just have to standardize 2.11 and 7.14 first. And we're going to get two values of z, which are negative 2.30 and positive 2.00. In other words, we're just simply trying to find the probability that your z is between negative 2.30 and 2.00. And using the norm disk table, we just simply have to find the cumulative probability of 2.00 and subtract it with the cumulative probability of negative 2.30. And that gives us 0.9665. Next is if you're trying to find the highest BUN among the population with the least 10% BUN. The least 10% BUN here refers to the area of 0.10 on the leftmost part of the distribution. And the highest BUN there is simply that x which is on the rightmost part of that region. And using the norm disk point PDF table, we know that the cumulative probability of 0.10 is when z is equal to negative 1.28. And since we know that z is equal to x minus mean over the standard deviation, all we have to do is to substitute z as negative 1.28, the mean is 4.80, and the standard deviation is 1.17. And by cross multiplication and transposing the mean on the other side, we're going to get a value of x, which is 3.30 millimoles per liter. And next, if you're asked to construct the normal reference range, or what we call the normal values for BUN, which is composed, for example, of 95% of the population. Now, all you have to do is to find z sub 1 and z sub 2, in which the area in between is 0.95. And we already found that a while ago, and those values of z are negative 1.96 and positive 1.96. In which, when z equals negative 1.96, with a mean of 4.80 and standard deviation of 1.17, we're going to find the value of x, which is 2.51 millimoles per liter. And similarly, when z is equal to positive 1.96, when the mean is 4.80 and standard deviation is 1.17 millimoles per liter, we're going to find x as 7.09 millimoles per liter. Thus, we can say that the normal reference range, which is composed of the 95% of the population, is 2.51 to 7.09 millimoles per liter. Now, this is the reason why in constructing the normal reference range, laboratories usually make use of mean plus and minus 2 times standard deviation when they want to claim the 95% interval, just like in the previous example. Note here that they are just using 2 instead of 1.96 for convenience. The empirical rule, also referred to as the 3 sigma rule or the 68, 95, 99.7 rule, is a statistical rule which states that for a normal distribution, approximately 68% of the observations fall on the first standard deviations, approximately 95% within the first 2 standard deviations, and approximately 99.7% falls within the first 3 standard deviations. In other words, we have approximately 68% or 0.68 as the probability of z between negative 1 and 1, approximately 95% as the probability of z between negative 2 and 2, and approximately 99.7% as the probability of z to be between negative 3 and 3. As for additional exercise, let's make use of the National Medical Admission Test, also known as the NMAT, in which it is said that for a norm group, the mean of the general performance or the GPS is 500 and the standard deviation is 100. And suppose you're asked to find the cumulative probability or the percentile rank of examinee who got a GPS of 710. And find the GPS of an examinee who got a percentile rank of 97%.
To answer the first question, which asks for the percentile rank of the examinee who got a score of 710, we just have to standardize 710 based on this mean and standard deviation. So the probability of x less than 710 is the same as the probability that the standardized score z is less than 2.10. And taking a look at the table, 2.10 is 0.9821. Thus, this represents the area or the proportion of the examinees in which his score is higher. Thus, his percentile rank is 0.9821 or 98.21%. On the other hand, if the percentile is 97% and you're being asked for the GPS, that indicates that if this is the normal distribution, 97% of that is somewhere here. And you're asked for this GPS score X. So we just have to find 0.97 on the table in which we can see is at z of 1.88. So we can say that the z-score of this is 1.88. Now since z equals 1.88, and we know that z is x minus mu over the standard deviation, substituting z as 1.88, mean as 500, and standard deviation as 100, cross-multiplying 100, and transposing 500 on the other side, we're going to have 500 plus 100 times 1.88, and that gives a GPS of 688. Thus, the GPS of the examinee who got a percentile of 97% is 688.
Now earlier in this video, I have shared that We Are Social and Hootsuite reported that last January 2021, the mean daily use of Filipinos in social media is 255 minutes or 4 hours and 15 minutes. Now assuming that the daily use of social media of Filipinos is normally distributed and the standard deviation is 30 minutes, find the following. If you learned in this video, you may click like, you may also subscribe and hit the notification bell for more videos soon. Just do not forget that whether you're on the norm or on the extreme side of the normal distribution, just be yourself and most importantly, be happy in everything that you do. Stay safe, guys.